Hello, my name is Emmanuel Mate and let me introduce the subject of my presentation, aerosol aging in the containment after an accident, work realized at the IRSN in collaboration with the PC2A, in the context of the Generation 4 initiative and more especially in France with the review of safety case undertaken by the IRSN on Astrid, future SFA reactor. It's necessary to study the source time during a severe accident. The objective of my presentation is to describe part of this research which concerns an aerosol numerical simulation of the contaminated sodium spray fire. This is my simulation of a sodium fast reactor. A large SFR has many advantages, but also two serious drawbacks. First, the high reaction of sodium with air and water, and the neutronic positive void factor. During a severe accident, all the security system malfunction. That has for consequences the core temperature overheating up to sodium boiling. Sodium bubbling can lead to the core disruption. The sedimentation of the core fragment can cause a sodium vapor explosion inside the primary sodium that could damage the rotating plug. This vapor explosion could inject in the containment a contaminated primary sodium spray, as you can see. We now zoom into an individual sodium droplet which has typically a size of 3 mm. In reaction with the oxygen of the containment atmosphere, an oxidation will occur on the droplet and form an oxide film. The reaction will cause the droplet heat up. When the boiling temperature is reached, the sodium vapor traverses the oxide film and burns in the gas phase. Only during this stage, aerosols are produced. It's essential to model the oxidation and the combustion to not overestimate the amount of aerosols. In other words, the oxidation phase fixes sodium oxide in the droplet. We study the aerosol because they are initially extremely toxic and their dispersal is a major issue in the source time analysis. We made a sodium spray fire numerical simulation based on the improvement to the model of TIE. You can see here the fall distance of the droplet before the combustion starts. Red point experimentation, blue point simulation. We reproduced TIE model and its result. We improved the model. For example, we had thermal radiation model. We had some correction. For example, we changed the heat conventions and we validate this new numerical simulation named NATRAC. The results show that around 60% of the sodium is transformed in aerosol. The aerosols are extremely toxic and it's only the aging that renders them not toxic. We know that the initial aerosols measure 1 micrometer and they are spheric. One detailed model of aerosol aging exists, Cooper, a layer model. The initial aerosol react with water vapor and carbon dioxide to form the hydroxide, the carbonate, and the bicarbonate. You can see here the evolution of the mass of suspended aerosol of peroxide, hydroxide, and bicarbonate. We calculate also the composition of the aerosol in function of the injection time in different conditions. You can see here right humidity of 50%. The first injected aerosols are highly transformed into bicarbonate, whereas after some time carbon dioxide is left and the aerosols are only transformed into hydroxide. You can see the result of right humidity 5%, slower gas diffusion into aerosol, and in a pool fire situation. You can see some significant difference in the phenyl composition that can have an impact on the radiocontaminant chemistry. So, we made a numerical simulation of the aerosol produced by a sodium spray fire. We made a numerical simulation of the aerosol transformation. We will make some experiments to validate the last numerical simulation, and we will make the numerical simulation of the radiocontaminant transformation. I would like to thank the people I worked with and thank you for your attention.